So today I'm going to be sharing a little bit about how I use ARM64 both in the cloud and on the desktop. This stream is actually brought to you from ARM64. So specifically, I think I can show you. If I go to Chrome About, I think it will. Chrome version. Hey, there we go, Chrome version. Let's show you what that looks like. Select screen share, one Chromium tab, about Chrome. So yeah, let's flip that back. I think you can see that now. Yep. So you can see that this is OS X Linux, Linux ARC64. So this is my everyday working environment. This is where I get the majority of my work done, and it is all running on ARC64. So unfortunately, I'm in the process of trying to show you how the rest of my desktop looks, except for I'm using Wayland, which artificially restricts things. So you cannot actually share the contents of another window or the entire desktop with an application, except for through a privileged process. And Ubuntu ships with that privileged process turned off for Wayland, which is unfortunate. Curse you, Ubuntu, curse you, Wayland. Otherwise, I'd be able to show you what my glorious desktop looks like. But in fact, it looks like a perfectly ordinary Linux desktop, which is kind of fun and exciting. So yeah, that is basically kind of the start of things that I wanted to show you. But let's actually show you what the physical box looks like. I think I can do it this way. Yep, there we go. So this is my ARM64 machine. And as you can see, it's a mini ITX motherboard, got some nice ports on the back. Really, really tiny form factor. Unfortunately, the networking ports aren't quite working, so there's a need for a dongle, but that's going to be fixed in a new firmware revision. It's got an AMD Radeon graphics processor, and yeah, that tiny little thing right in there, that's a knock to a fan that's covering a very tiny, that's covering our processor. It's a very tiny processor. It's about 35 watt TDP. And it's 16 cores. So in a moment, I'm going to see if hopefully finishing recompiling XDG desktop portal works, so I can actually show you that. In the meanwhile, why don't I just go ahead and show you part of what Honeycomb looks like, part of what our production environment looks like, to kind of branch out from ARM on the desktop to ARM in the cloud. Also, I should probably pop open the Twitch chat. I'm sorry if you put anything in the chat earlier, I missed it. So yeah, basically, ARM64 is, okay. ARM64 is what we use in part in the cloud. So let me filter these instances so that I'm only showing you what I intend to show you. Just filtering this. Architecture is 64-bit ARM. Yep. Okay, so now it's safe to share this tab. So I'm going to share one browser tab with you. What I'd like to share with you is my EC2 instance list. So we have a number of hosts that are running on ARM64. I've got a collection of M6G instances that are Graviton 2. I've got a collection of A1 instances that are Graviton 1. So as you can see, we've got some mixture of our ingest pipeline and our UI serving pipeline that is currently operating on ARM64. And one of the fascinating things is I can actually show you apples to apples. Environment is Kibble, and role is Shepherd. So I can actually show you apples to apples. Here's a C5 instance versus a M6 instance. And you can actually see here that the C5 instance has noticeably higher CPU utilization compared to the M6G instance. Let's see, where's the legend for this graph? Oh, please show me the legend. Is it here? Yeah. So you can see here, the C5 instance is orange, the M6G instance is blue. So unfortunately, we're still running in a mixed configuration, so I can't actually scale up our M6G instances harder, but you can see that it's about, indeed, as does what it says in the tin, it's about 20 to 30% performance improvement. Other cool stuff that I can show you that relates to that is just get a two-factor code in. Auth two-factor 372522. Oops. Wait, you just see a blank screen? One sec, let me, oh, shit, I'm so sorry. There we go. Is that better? Now do you see what I mean to? Let's go back and I'll show you that to you again. So let me just go back a couple steps. Thank you for pointing out that I was just sharing a blank screen. That would have been horribly embarrassing. So as you can see here, this is Shepherd. This is our ingest service. I'm comparing a couple of our M6G instances with a couple of our C5 instances. And I'm going to CloudWatch to compare the CPU utilization. As you can see here, the ARM instances are running at about 44 45% CPU utilization, and the AMD 64 instances are running at 51 to 54% CPU utilization. So that's about a 25%, percentage-wise performance difference. And then if I go through and look at the honeycomb view, what I can see is, let's go over to here. Let's see. This is system stats. And if I launch a new query and look through my history, let's see. So Shepherd environment is cable group by machine type. Yeah, that should do the trick. So you can see here, machine type is not set. Let's try instance type. There we go. That'll do the trick. Let's look at 14 days of data here. And you can see that I used to run our M6G instances super hot, and I could run many fewer of them. So in fact, let's serve up a count here so we can see how many there are. So you can see here that we used to be able to stably serve, this is actually count distinct host name. Here we go. So you can see here that we used to be able to serve this entire workload off of 7 M6G large instances. And since we turned those down and replaced them with C5 and C5D, C5N instances, you can see that it's taking a total of 10 plus instances, peaking at 13, 14 instances to serve that same workload that we are serving on M6G with only 9 instances. In fact, let me set this to stacked so you can actually see the difference. So that's the concrete difference, is we're able to run with the same latency M6G, we can run it hotter, and whereas on AMD 64, we have to run more instances at lower CPU utilization to achieve the same results. So that's kind of a little bit of detail about our cloud environment. Let me see if I can install the package that I think will enable me to actually properly share my screen. Nope, still no such interface org free desktop portal screencast. That's annoying. Okay, so we'll have to work that detail out some other time. So you might ask, how much trouble was it to port this stuff over to run on ARM64? And I can actually concretely answer that. So let's show you what that looks like. So if I go and look at our Circle CI configs, I can show you exactly what it took to make our Golang program compile both for ARM64 and AMD 64. So specifically, you can see there is a flag here that basically says, for my Go build, I want to build for both ARM64 and for AMD64. So there's a step to build on AMD64, and there's a step to build on ARM64, and they're templated nicely. So if I open the, if I search for Go Arc, you can see here that it's just a parameter that defaults to AMD64, and I just export that environment variable, and Go will build an appropriate binary. And then for distributing it, we have a custom workflow here that basically says, move all of the binaries that are created in the foreign architecture folder, Linux ARM64, and put them into a special tarball. So we're shipping one tarball for ARM64 and one tarball for AMD64. And then our deployment scripts, popping over repos, what our deployment scripts wind up doing is they fetch that data out of the correct location. So if I look at our chef scripts, I think this is update deploy. Is this called update deploy? No, update deploy sets which version is current. I need what? Where is deploy.sh? It's in here somewhere. Yeah. Deploy honeycomb service. Here it is. So deploy honeycomb service here. We'll go ahead and say, hey, I'm role X, I'm environment Y, and the only sign that you're running on an ARM64 machine in production is a little flag that says my architecture is $architecture. Or $architecture is, ARC64. It's whatever uname-m returns. So again, hey, by default, we fetch the AMD64 artifacts, but if we are fetching ARM64, then we fetch from a different artifact path. And then we go ahead and ntar it and restart the service, and the binary just seamlessly runs. It's kind of cool. But that isn't the entirety of the story, because we also had to make our machines bootstrap. If you were using something like Kubernetes, it would be pretty seamless and painful, because every container would be initialized with the correct container environment. But in our case, we deploy on raw machines, which hurts us a little bit. So we had to change a bunch of our shell scripts and our Chef Ruby scripts. For instance, if I look at our cookbook, our cookbooks actually have flags that specifically say, hey, by the way, if you're pulling down our tool that scrapes logs into Honeycomb, then you have to fetch the appropriate download URL depending upon whether you need to fetch the ARM or AMD64 binary. The same thing is true for OS query. By default, we install from package.osquery.io on AMD64, but we built our own ARM64 copy of OS query, which we use to do system auditing, and that had to be built specifically for ARM64. Same deal again is true for things like things like the AWS inspector. Again, the AWS inspector, it's a architecture specific binary, so you kind of have to choose which one you install. So that's pretty much the amount of work that it took to glue this stuff together in order to make things work on AMD64 and ARC64 together. So let me see if I can stop streaming that. Let me see if I can, instead of trying to share something that way, let me see if I can just, I know what I can do. This is going to be super janky, but we'll do it this way. So here's my desktop, and here's the terminal, and I can run, for instance, screen fetch. And you can indeed see that it, fetches a bunch of details about my system and then reports back and says, hey, Liz is running Ubuntu 2004 with 16 ARM Cortex A72s. And let me show you what else is running on the system right now. So obviously there is a bunch of Chromium tabs, but also I am donating cycles to the Rosetta project, really cool project. So the Rosetta project is a effort to fold proteins, to figure out the optimal ways that proteins fold. So it's kind of like folding at home, but this particular lab, the Baker Lab, has been doing a bunch of COVID research to design better vaccines, to design better mechanisms to target the spike protein, the SARS-2 spike protein. So I'm proud to say that I've contributed in some way or another to this, which is super exciting. So I keep it running all the time because, as I said, this thing back here, it only uses 35 watts of power. So it's, really, really thrifty. I'm happy to have that added onto my power bill. So yeah, 16 cores, 16 real cores, not hyperthreads. So the equivalent of this system is actually a 32 core system, 32 hyperthread system that you might get off the shelf that might cost you thousands and thousands of dollars. And I happen to have loaded into it 32 gigs of RAM. It supports ACC RAM, which is particularly exciting for nerds. And yeah, so that is kind of a little picture of what the system utilization looks like. So I guess I can show you the other little bits that I have open. So you can see kind of over here, I've got a bunch of Slack tabs. I've got a bunch of Google Docs open. But yeah, mostly I'm just, working in the terminal. So yeah, this is unfortunately a really awkward way to do screen sharing, but we just have to roll with it. Okay, so let me show you. Really wish I'd brought the tripod up from upstairs. Let's see. So I can show you the build process, which just works seamlessly on. Let's see. This is Honeycombio Hound. So this is our source directories, and I can just run, go build, or sorry, I can just run go install, and it will do the right thing. So I can build our web front end, and it's pretty fast. So it just runs pretty much instantly, or as far as you can pretty much instantly build a giant source tree that's been built up over many years. So let's see, if I run time go install dot, how long does it take? Oh, it's cached now. That was a silly test. But yeah, so, and then also we can do things like run Node.js as well. So I run yarn build. That just, works completely out of the box, works just fine. And all of that toolchain is completely unmodified. It's just all components have been fetched out of the Ubuntu repository. So that's kind of a little bit of a tour of my development environment, which is, standard Linux command line as far as anyone's concerned. The one caveat to be aware of is this is 16 real cores, but each core is only clocked at 2.2 gigahertz. So single core performance really does suffer versus other applications. So my, it's never going to crunch a single-threaded workload as fast as my Intel machines that I have, but it's pretty decent. It's definitely pretty tolerable for ordinary working. Let's see whether my machine cries under this load or not. So for instance, as you can see, the graphics acceleration is perfectly fast. If I pop open GLX gears over here, then you can see that it works perfectly fine. GLX gears is perfectly smooth, although it's pegged to 59 FPS. So yeah, so that's, that's how I do my day-to-day work. So I'm going to flip back over to Ready Face and, I'm happy to take questions that people have about like what was it like to port to ARM64 both for my desktop, what was it like to port to ARM64 in the cloud, and any other questions people have. By the way, my build of our front end just finished. 104 seconds, perfectly reasonable. Actually runs faster than running on Circle CI AMD 64 machines. Meanwhile, while I wait for questions, I'll go ahead and try to again fix my damn fix my damn pipe wire. Yeah, hey Jeff. Yeah, so I have a giant honking AMD 64 machine here under my desk that has the pants beaten off of it by the tiny 35-watt ARM64 machine. Granted, this machine here under my desk is, I think, a 2016, 2017 era processor. So it's like something like a 16 or 18 nanometer process. But on the other hand, the ARM Cortex-72 is actually pretty similar in terms of the transistor size. So this is actually a pretty decent apples to apples comparison of what the ARM architecture can do for a given number of nanometers of transistor size. And as you can imagine, the more modern ARM N1 cores that are used inside of the AWS Graviton 2 processor, right? Like that's, I think, 10 nanometer process, 12 nanometer process, so substantially more modern. Is OBS using VA API for encoding? I actually don't know. What I'm showing you now is from within Chromium. This is using Lightstream, so go lightstream.com. So it is using VA API, I think, because this copy of Chromium is enhanced to use VA API for both displaying video and for encoding video. Nice, 7 nanometer. So yeah, I am farming out a bunch of this workload off to Lightstream servers, particularly the transcoding workload. But the source audio and visual feed, right? Like it's pretty smooth. All of that kind of source audio visual feed is done through this ARM chip sitting right there, and it is pretty buttery smooth as far as I can tell. Have I bumped into any surprising performance differences? Honestly, the thing that really surprised me is we tested using Graviton 2 for our storage and query backend, and we were really, really worried. We used things like XX hash that rely on AMD 64 intrinsics and on hand-optimized assembly. It turns out that even without hand-optimized assembly, the Go compiler for ARM64 generates code that is faster than or just as fast as the AMD 64 hand-optimized assembly. So that was the real surprise, was that you think that you depend upon AMD 64 intrinsics, but run benchmarks. It really, really might surprise you. It might be just as fast because the ARM64 processor instruction set is different. The instructions per cycle is slightly different, right? Like, so you can actually essentially, I don't know under the hood how much money this concretely saves Amazon, but I don't know how much money it saves Amazon, but I know that at the end of the day, hi Lightstream, please update. Okay, cool. Hopefully that comes back. This is why I proxy things through Lightstream. Lightstream servers keep my Twitch connection alive. At the end of the day, comparing apples to apples, right? Like, 200-watt machine here, 75-watt machine here, including the graphics card, right? So kind of, it's effectively saving Amazon 50% or more of the power bill versus a comparable AMD 64 machine. And then in addition to that, they don't have to pay Intel for the kind of overhead of Intel charging for the IP development, right? As far as I know, ARM charges like a licensing fee to anyone who builds chips based off of their designs. But, it's substantially less overhead, and it's a lot easier to bring that kind of whole supply chain in-house, which really, really reduces the cost to run servers that are based off of ARM64. But pricing wise, basically AWS has set prices at 20% lower than comparable AMD 64 machines. So I'm quite happy to take the 20% price decrease and the 30% performance increase, even if I know secretly that it's probably actually more saving Amazon more than 20%, and probably Amazon gets better margins. That's my suspicion, and I know that Jeff's probably zipping his lips here, but it's compelling enough for me that it was well worth the effort to switch. On the desktop wise, yes, the on the desktop, it's a little rough. There are some rough edges. I wouldn't recommend it yet for a generalist developer audience. John Nettleton, who's in the chat, is one of the developers of the Honeycomb ITX board, not to be confused with Honeycomb, the product that I work on. But that board right now is $750, and then you have to buy a case and you have to buy memory. So all in, it's like $1,000. But so it's slightly less beefy than if you were to build a machine based off of a AMD EPYC processor. But it's definitely much less power hungry, and there's a lot of geek cred associated with doing your work on an ARM64 machine. For people who want to try this on a less expensive setup, you can just get a Raspberry Pi 4. A Raspberry Pi 4 is, I believe, also the A72 processor, but it only has, I think, 2 or 4 cores rather than 16 cores, and its memory is hardwired to, I think, maximum of 8 or 16 gigs. You kind of can't use it to do heavyweight duty, like recompiling Chromium or like recompiling Linux kernels. That will take hours and hours and hours. Whereas for me, I can recompile a Linux kernel. Like I can, I'll leave it to sit for 45 minutes, 60 minutes, and it's done. So you can really see that difference because I know that the Ubuntu build farm that powers Launchpad uses Raspberry Pis. They just literally have racked a bunch of Raspberry Pis. So a Linux kernel build that takes me 1 hour to do here will easily take 4 or 5 hours on the Ubuntu build farm. But that's kind of, they don't yet have access to Honeycomb ITX boards. I dearly love it if someone would hook them up either with Honeycomb ITX boards or like if Packet could hook them up with the Ampere Ultra machines, because those are much more ergonomic for actually getting like heavyweight compiling work done. Yeah, so it is kind of a fully bootstrapped system. You don't need anything other than write to an SD card, and then after you've written the firmware using an SD card, everything else can be kind of compiled on ARM64 for ARM64. And yeah, as far as the coincidence of the names, I certainly cannot say that I wasn't influenced at all by the fact that the names were the same. But also, the Honeycomb ITX board really genuinely is the best ARM developer board that's out there right now. Because every single other competing board is, a server desktop tower that'll set you back $3,000, $4,000, right? That's not really appealing to people who just want to tinker. And the Raspberry Pi is, yes, it costs $40, but on the other hand, you kind of get what you pay for. It's not really usable for day-to-day work. The graphics acceleration is not really that great. The ability to handle massive compile loads is not really that great. So yeah, that's kind of how to get started with ARM64 is, get a piece of hardware that supports it, install an operating system, and get going. Oh God, $13,000. I don't even want to think about $13,000. Like I like messing with neat architectures, but not to the tune of $13,000. See, what are the other fun little things that I can show? I might at some point do a follow-up stream once I'm actually able to properly share my entire desktop with you all. But unfortunately, that day is not today. When are others going to do ARM64 instances? I got bad news. So Google has been advertising PowerPC-based instances, but they cost you, like hundreds of dollars per hour, as far as I know. They cost hundreds of dollars per hour, and it's power, right? Like it's it's useful for some high performance computing, but it's not kind of a generalist environment. And as far as I know, I left Google a year and a half ago. I can I've been observing Google from the outside for the past year and a half. So can confidently say no inside information here that, I haven't seen any signs from Google that they intend to do ARM64. Google does have an internal hardware lab, but it's not nearly kind of the same level of sophistication as Annapurna Labs, which was acquired by Amazon. Microsoft might actually do it. Microsoft certainly has been investing in ARM64 support. In particular, Microsoft has released a bunch of versions of Windows for ARM, which make me think that at some point they have those test benches of hardware running. They're running enough ARM64 at scale that they could potentially offer it in Azure. But at the moment, if you want ARM64 in the cloud, Packet and Amazon are kind of your only two games. Packet is kind of more similar to DigitalOcean, right? Like they'll sell you hosts or VMs, right? Like they're not a kind of full service, EC2, EBS, all of those value added services. But I have to say it's really, really compelling to not pay very much money for my company's cloud stuff anymore. Although instance availability is a little bit of a sore spot. Right now in US East 1, I believe only 3 or 4 out of the 6 or 7 AWS AZs in US East 1 have ARM64 in quantity. So you can get A1 instances, the previous gen of Graviton, in all AZs, but you cannot get Graviton 2 in all AZs. So, pick the right AZs. So we're actually having to migrate AZs in order to get the full benefit of Graviton 2 everywhere. Let's see. Oh, other little bits of hardware kit I should show you. So I can show you this. So this right down here, is my KVM. So it enables me to swap between my desktop, between my AMD 64 gaming kind of desktop and my work-focused ARM64 machine. So I have one set of monitors, one keyboard. In fact, I share even the webcam and the mic between both of my servers here. It's kind of a mechanism to. It's a mechanism to easily swap back and forth without having to replug cables or like splitting one monitor and the second monitor. So I think that's kind of really, really essential. The other bit that's really, really essential is with a piece of prototype hardware like the Honeycomb ITX, you will inevitably make it enable to boot or enable to display graphics at some point. So there is a serial console. There's serial console over USB. So I actually have my AMD 64 and ARM64 boxes connected via a serial console cable, so I can actually debug via remote serial console instead of needing the display to always work. Display is based off of your graphics card. So my AMD Radeon card that I bought is 4 mini display ports, but basically any graphics card will work. Although the NVIDIA drivers I hear are a little bit more dodgy on ARM64 because you only have the open source Nouveau option. But yeah, there is no onboard graphics by default. So if people don't wind up using their Honeycomb ITX for kind of desktop work, they can just not buy a graphics card, always use Serial Console until they've set it up for SSH and just put it in their basement and use it for compiles. But personally, I happen to like being able to actually say that yes, I use ARM64 on the desktop and do my web browsing and so forth from there. The other thing that I've done to kind of make things a little bit easier is, let me see if I can share this really fast. There are NVIDIA ARM64 binaries, says John, just not super ready yet for this platform. Okay, let's switch here. All right. So the other thing that I've done is I have created a bunch of Ubuntu PPAs so that people don't have to rely on the. Did that not work? Camera, screen switch, updating stream. There we go. So I created a PPA that lists particular kernels that are compiled to work with the Honeycomb ITX. So for instance, there is a custom build of the Linux kernel, and it is verifiable because you can see what the source code is. You can verify that I haven't monkeyed with the source code. So in particular, there are a couple of things that need to be backported to make the graphics card boot correctly with your kernel. There are a couple and upcoming networking patches that will be in this PPA, so you don't have to compile your own kernel. And similarly, I keep a bunch of other random backports and things, for instance, to make the screen fetch program print your processor ID rather than just saying it's an unknown ARM processor. So that kind of makes it easier. Yeah, overall, I think in reference to the thing I said earlier about like benchmarking, like, yeah, you got to do it. We spend a lot of time with Honeycomb, actually specifically visualizing how long does it take to do each operation, which operations are sped up by, which operations are slowed down by, which operations are slowed down by running on which architecture. So we did a lot of kind of comparison of traces and so forth. KVMs, yes. This KVM is a TrendNet KVM. It's a little on the pricey side, and it is natively DisplayPort. So it takes 2 DisplayPort in, and it output from 2 different machines, and then it outputs to DisplayPort. Open source projects that are waiting on ports or optimization for arm64. I think the main one, which I talked about earlier, is OS Query. So there are some outstanding issues there. Specifically, black screen. Yep, there we go. So there's a open issue in OS Query to port and maintain the continuous build on arm64. In particular, there were a bunch of things that needed to be changed. What did Artemis do? Let's look at the diff. There were a bunch of changes that needed to be made in order to support the architecture, in order to support the architecture on all of the dependencies, because OS Query is something that's designed to run with very few dependencies, so it has to compile everything from scratch, and it also relies heavily upon what syscalls are available. So that's something that took a bunch of effort to port over. So this is not, we currently are running a fork. We're not very happy maintaining that fork forever. So at some point, that'll need to be merged into mainline. So that's kind of one area. What other areas am I aware of that are kind of painful? Like, because Honeycomb is in the Go ecosystem, a lot of our stuff, basically just works, and the Go compiler has abstracted all of that away from us. Have we run M6Gs in EKS? No, we have not run M6G in EKS because we are not Kubernetes users at Honeycomb, or at least not for production workloads. Oh God, you want to run, Kafka cluster. Okay, Kafka cluster and not Kafka cluster running on EKS. I was going to say, if you're running Kafka on Kubernetes, you are like, you're setting yourself up for a lot of pain. So yes, we heavily use Kafka at Honeycomb. Right now, our Kafka machines require lots of local SSD, which at the time was only available on i3 and i3EN instances. And still, there is not a ARM64 with lots and lots, as in terabytes of SSD. There's no ARM64 terabytes of SSD, so our Kafka brokers have to stay on AMD 64 for the foreseeable future because of just the instance sizes that Amazon offers. But I can vouch to you that I have in fact run Kafka on my local host here on my ARM box, and it works fine. because it's just Java, right? Like Kafka is just a Java application. Zookeeper is just a Java application. So it seems to work fine. Haven't extensively performance load tested it. And as far as Kafka producers and Kafka consumers, so our ingest pipeline is a Kafka producer, right? It reads data coming in JSON format from the public internet and writes it with a Kafka producer to our Kafka cluster. That actually, as I was saying, it runs faster on ARM64 than AMD64. I don't know what fraction of that is the actual Kafka producing versus what fraction of it is just mangling and parsing JSON. The mangling and parsing JSON is pretty much the ideal case for ARM64, right? It's just straight up, manipulating data. And then on the consumer side, our indexing servers actually consume off that Kafka feed. And again, performance does improve when you move to M6G, or actually we were trying both M6G and R6G. So our experience says that, yes, the Kafka consumer and producer libraries in Go are perfectly performant on arc64. Rust. I have not actually run any Rust programs on my ARM machine, mainly because I'm not a Rust coder. We don't really use Rust that much at Honeycomb. It would be really exciting for sure if it got first-class support in the language runtime, but that is outside of my world. The one pain point I think with regard to Kubernetes that I should mention is mixed fleets. If you are in the process of transitioning from AMD64 to ARM64, you need to set up separate jobs, I believe. Schedule separate jobs in Kubernetes for your ARM64 and AMD64. As far as I know, Kubernetes doesn't let you specify use this Docker image for ARM64 and use that Docker image for AMD64. The same thing is also true for our auto-scaling groups, that you cannot mix, you cannot have conditional, use this AMI for one architecture and use this other AMI for the other architecture in the same auto-scaling group. There is one launch config, and you cannot mix different instance types. Really painful, really annoying. So when we were in that transition period, we actually had to have two different auto-scaling groups. But then that created the potential for feedback loops. So we wound up ultimately saying, you know what, we're going to clamp the number of AMD64 instances to a fixed number, and then we're going to auto-scale the ARM64 instances. So both auto-scaling groups can be part of the same target group, but you can't have them mix the scaling aspect, the EC2 scaling aspect. Eventually that'll get better, I'm sure. But right now the transition path is a little bit sketchy in terms of needing to conditional things or run more than one ASG. And that same pain is also felt in the Kubernetes, scheduling on ARM64 versus AMD64 pods. Your Docker image will not work. The same Docker image will not work across both arcs. Any other questions? What was your exploding galaxy brain, Ariel? I got a question on Discord actually, rather than on Twitch. Someone was asking, what's the Go library that should be that should work on ARM64, but right now is ARC specific. It's called XX hash. It is a mechanism. It's a non-cryptographic hash that aims to be really, really fast. So it gets used for things like Bloom filters, other kinds of really quick deduplication or other indexing of data. And yeah, if you're going to run Kafka on Kubernetes, read the excellent tech blogs that the team at Confluent have put together. But yeah, I would not recommend. It's similar to running MySQL on Kubernetes. Persistence of Kubernetes is very, very fickle. So just be careful you don't blow off your own foot. Why can we not run AMD instances at full load? The answer is the AMD instances slow down and contend on CPU the hotter you run them. So if you run them at 60% median CPU utilization, or sorry, if you push them from 60% median CPU utilization to 70% median CPU utilization, because they're just less efficient than the ARM processors, a small spike in workload will result in the CPU becoming saturated, which results in queuing, which means that we will start failing to meet our target of 5 to 10 millisecond ingest times, and it'll spike to 100 milliseconds, 200 milliseconds, right? And at that point, it starts getting really, really bad. Because if our customers are transmitting telemetry to us, we don't want their queues to get full, because then they'll degrade the performance of their apps downstream, right? Like, we bear our responsibility as a service provider very, very seriously. So we want to make sure that we're always quickly ingesting telemetry, which means that we don't just care about the median latency, we care about the 99% latency, the 99.9 percentile latency, and so forth. So therefore, we have to run our AMD 64 instances cooler than we otherwise might in order to give them that headroom for bursts and prevent the latency at the 99.9th percentile from degrading. Whereas on ARM64, we can comfortably run them at 60-70% CPU utilization, because there is much smoother tail latency. There's less variability in what other neighbors might be contending. They don't use hyperthreads, right? Every Graviton 2 core is at a real physical core and not a hyperthread of a CPU. So it means that the performance curve is much. If you look at the performance curve, you'll notice that the latencies and the CPU utilization are both a narrower curve, and it's shifted to the left, right? Or my left, your right, whatever. It's shifted to the left, right? Like, it's shifted towards being lower latency. It's shifted towards being lower CPU utilization on the same workload. So that's kind of why, when I was showing you the graph of CPU utilization earlier, you could actually see visually, right? Like, that the median CPU utilization, I was able to push it higher without clipping to 100% CPU saturation at any point. And that guarantee just isn't there for AMD 64 instances, because they perform worse, they have more variability. So that's why it's clearly a win for us to use ARM64. Hope that helps. So if it were a non-latency sensitive workload, peg the CPU, but we have a latency sensitive workload, and that really influences how we think about our architectural design. That being said, we do make heavy use of AWS Spot, so we can scale up during the day. So we actually run at 50% utilization of our AMD 64 instances all the time. And we just add or remove machines as we need. And the same is going to be true for ARM64. Just again, availability of ARM64 and Spot is a little bit limited at the moment in some availability zones. So Spot instances can mean that each machine is utilized 50% or 60% or whatever, and you take away or add machines to keep that true. Yeah, so hopefully the next time I do a stream like this, there will be a little bit better of a mechanism to show you my desktop. How many ARM64 nodes am I running? So my personal ARM64 machine is one machine there. I happen to know that this Google Pixel 3 has an ARM64 processor inside it, so okay, we'll call it 2. In terms of Honeycomb, we operate, when we get fully migrated over and solve the availability zone issue, we will have several hundred M6G or R6G or C6G instances. We'll have several hundred of them in the X large size. So it'll be pretty great when we get there. But we kind of have to migrate workload by workload. We've got a little bit of prep work to migrate into the AZs that have ARM64 nodes. And when we were testing Graviton 2 during the preview process, our benchmarks were all on approximately, we were testing on approximately 50 to 100 nodes at a time of ARM64. So, we're not necessarily the biggest users in the world of ARM64, but we're also certainly we are some of the earliest users of Graviton 2, thanks to the folks at Amazon giving us access to the beta program. And yeah, so what's the timeline here? I guess we were invited to the beta program in February or March. So I used ARM64 on the server first, and then I ordered a Honeycomb ITX board from Solid Run about a month or two later. It took 2 months to turn up, so in May I started being a desktop ARM64 user. Did we have some Graviton 1? We deployed production workloads to Graviton 1 first. So our web app tier, our front end, is running entirely on Graviton 1. And it's not a performance-sensitive workload. It was just clearly a case of, these were T3 instances before. Let's just move them over to A1 instances. So we haven't done a comparison apples to apples in Graviton 1, but I'm pretty confident we just wouldn't want to run Graviton, run our latency-sensitive workloads on Graviton 1. That just doesn't make sense. Whereas Graviton 2 was the first thing that actually was worth seriously considering versus our Intel instances.
Care at all. He's unaffected. Not like Natalie. Right.
Yeah. So, other fun things about this case, by the way, back here. It is a 4.5 liter case. It's super, super tiny. It's super, super portable. So if I didn't care about wanting to have two monitors, I could actually pick this up and taken it down to my streaming studio downstairs. But unfortunately, I'm a little bit lazy about it. So I was like, you know what? I don't want to unplug these cables and reboot the thing. I'm just going to do it here, and I'm going to use my phone to show to show what the board looks like. Let's see whether I have any Discord questions or anything. Nope. That looks like the questions that people have left for me. Nothing in the AWS channel. Oh, by the way, one thing that you may find helpful, there is a ARM developer ecosystem Discord. Highly encourage people to join it. I don't know, John, whether you can produce an invite link and stick it in the chat. That would be super helpful. Yeah, I love educating people about kind of what are the cool things that we're doing, both observability-wise and systems architecture SRE-wise. And I think really that ARM64 is a adventure that a lot of SREs should be embracing because it's the opportunity to get improved performance at lower cost. And that's kind of a thing that is super, super critical, especially in this economy. And market for desktop docks. Yeah, I happen to think that my that my KVM switch is fine, but it's a little bit pricier than I otherwise would like. If I were willing to tolerate non-DisplayPort and just do VGA, I'm sure that I could get like a $50 or $100 KVM switch. With this KVM switch, unfortunately, was like $150. So it is what it is. As someone who is a software engineer, I realized that the time savings was well worth it because I value my time at several $100s per hour. Yeah, okay, awesome. John has linked the Discord link, so you can find out more about Solid Run and the Honeycomb ITX. You can find out more about AWS Graviton. There are AWS and Solid Run channels on that Slack. So, yeah, awesome. Thanks for tuning into this hour kind of more freeformish broadcast. I might start streaming, kind of just doing co-working type streaming over the next couple of weeks, hosted from here, but kind of not necessarily something as focused on educating people specifically about ARM64. And yeah, indeed, folks from Amazon and from Solid Run were on this, and from Packet were on this call. So, feel free to hit them up. They're also on that Discord. They also love telling people about what they're doing.